Good morning, everyone. Let's go over this warm-up here quick. This is based off of the integral properties that was discussed in the video that you were supposed to watch on Wednesday. If you did not watch that video, um, we want you to go back, make sure you watch it. It is an Ed puzzle, and there's a link on our Wednesday Schoology page. So you can just go ahead and follow that, or just log into Ed Puzzle, and it'll be there assigned already. But what it basically talked about was, what if I know facts? So I know that the area underneath the curve of the function f of x from -2 to 7 is 13, right? So that's kind of like a given fact. We also know that of the same function f of x from -2 to 3, the area under that curve is -5. And then of a different function, g, the area under its curve from 2 to 7 is 3. So knowing these three facts, that's going to allow us to solve these problems. And what it gets at is it gets at the properties and not so much the antiderivatives, because we don't know what f is, so I actually can't evaluate this using notation. However, I can use the facts to find out the information given. And this one, the first one's kind of tricky. So we want to find the area under the curve from 3 to 7 of f of x. Well, I know the area under the curve from -2 to 7, and I know the area under the curve from -2 to 3 of f of x, so I can use these two facts to help me solve this piece here. Now, here's the way I think I would write this, and I'm going to focus on the properties. Part of this warm-up today is so we can review these properties that you watched on Wednesday. So if I take the area under the curve from -2 to 7, well, that's the exact same thing as going from -2 to 3 of f of x plus, well, then I have to finish, because here I'm going from -2 to 7. Well, this goes from -2 to 3, so then I would have to finish by going from 3 to 7 of f of x dx. Okay, well, let's take a look at what we know. We are looking to find this value right here. So I don't know that. However, I do know from -2 to 7, that's 13. So I'm just going to replace what that's equal to. And then I also know from -2 to 3 of f of x is equal to -5. So then the only piece that I don't know is the area from 3 to 7. And now this just becomes an algebra problem. You can kind of think of this almost like a variable, right? You got to find out what this whole thing is equal to. So really quick, do some quick algebra. Add 5 over to the other side. And I end up with 18. And I go from 3 to 7 of f of x dx. And that's how much area would be under the curve from 3 to 7 of f of x. So that might be the trickiest one. Now, I would mention right away that if this was a multiple choice question on a free response, I wouldn't show any work, and I would kind of just take the 13 and subtract a -5, which is like adding, and that's how I got the 18. So you could do this in your head, but I think it's important to write it out first couple times you see it. All right, the second property was the one that we had brought up about a constant multiplier. So look at this. We have pi. None of these have pi in them, so I can't directly use this as given. However, we had a property that said we can rewrite this. And just like we had with derivatives, if there's a constant, you can pull that constant out to make this problem appear different. And the reason why we would want to pull that out is now I know the area under the curve of -2 to 3 of f of x dx is equal to -5. So I know that this whole thing right here can be replaced with -5. And then I have to multiply that answer by pi. So this answer is just -5 pi. Okay, nothing super tricky there. Anytime you have a multiplier, sometimes it's friendlier to pull that out. Okay, the next one, I'm just going to pull this stuff down here. This, this one right here is the property that says if you have the subtraction of two integrals, then it can be separated from each integral evaluated from the same bounds. So I would rewrite this as the area under the curve from -2 to 7 of g minus the area under the curve of -2 to 7 minus f of x. So now notice, why did I have to officially rewrite this? Because I cannot use this fact of substitution until I know exactly what these are equal to. So -2 to 7 of g of x, -2 to 7 of g of x is right here. That's equal to 3. And then -2 to 7 of f of x, that's this one down here, that's 13. And when I subtract, I get -10. So nothing super crazy there. This one, the last one, please make sure you are writing this down if you didn't get it. This is the one that probably students make the most amount of mistakes on. And I believe Mr. Waffler showed this one in the video. It actually has a combination of two rules, the rule we used in part B and the rule we used in part C. We have to be careful with how we do this because this 4 is a multiplier. However, it's only a multiplier for f. It is not a multiplier for 3. So watch how I do this very carefully. I'm going to split this up first using the fact that, and actually I might save a step here. You'll see using the smartboard why this works the way it does. So the first thing I'm going to do is use the fact that if it's subtraction or addition, we can split this up and evaluate each piece, each sum, at its own bounds. Okay, so that's the first piece. Now, within that same step, notice this 4 only belongs to this integral. So if that 4 only belongs to this integral, then we can pull the 4 out as it was a multiplier the same way we did with the pi. Okay. Well, the benefit to doing that is that 4 is a multiplier, and then we know the answer, this part right here. The area under the curve from -2 to 3 of f of x dx is -5. So there's nothing too crazy there. But here's where the big mistake comes from that most students end up making right here. We do not know exactly what this answer is from our given facts because this is with f of x, and g of x. 3 isn't any of those. So now we have to evaluate the same way we did using the fundamental theorem of calculus. I got to think to myself, okay, whose derivative gives me 3? That's 3x. And then I have to evaluate it from an upper bound and a lower bound. And by the way, since we're doing an actual antiderivative here, I'm going to make a quick reference to the quiz that you took on Monday. Notice how if I take the antiderivative, I do not write the integral symbol anymore. A handful of people had done that on the problem you had to submit as a free response question. So that's poor notation. If you're putting an integral symbol in front, that means you have to still take the antiderivative. And that's what we did to get the 3x. So instead of the integral symbol, that becomes a straight line, which tells us to now just evaluate the upper bound. So we're going to plug 3 in minus the lower bound, where we plug in -2. So we do really want to pay special attention to proper notation here. Okay? And then I can simplify this. We know 4 times negative 5 is negative 20. I know this will be 9 minus 6, but it's subtraction of a negative, so it's actually addition. And then we get 15. 15 plus negative 20 ends up being the overall answer is negative 5. Okay, so just be careful. We can mix the antiderivatives with the properties of integrals, and you have to know how and when to do those separately. Part of today's Delta Math will have a question very similar to this in there, and I had a handful of kids really get stuck on what happens if there's a constant or even more. What if it's 3x to the fourth? You can still do the antiderivative of that piece and get an answer. Okay? All right. Really quick, speaking of that quiz, there was an error and I caught it a little too late. So I just want to make you aware of this, that if you took the quiz when you were supposed to on Monday night, and then I ended up grading it, I think it was on Tuesday. This specific problem had an error, and I must have mistyped. This was a drop-down menu. It actually did not have the correct answer in it. So what I did was, if you answered this question, you got full credit for it. But I would encourage you to go back and look at this specific problem, and we'll talk about it here really quick. A particle moves in a straight line, and its velocity is given by this function. Okay, what is the displacement? Which displacement is just the area under the curve from 0 to 3 seconds. So you were expected to set this up as the area under the curve of the integral of velocity, which the velocity equation is 5 minus e to the t. So then once you have that, now you had to evaluate it and find the antiderivative of each piece here. So the antiderivative of 5 is 5t. The antiderivative of e to the t is just e to the t. And then we plug in from 3 to 0. So here's my upper bound evaluated. Now notice this says 2 variables, so I've plugged 3 into both of those. And then we're going to subtract the lower value. Now this is the part that I think a lot of students usually end up making a small error on. It's right here. So that's why I'm going over this one, is what happens if I plug 0 in for t? Well, 5 times 0 is 0, but e to the first power, or excuse me, e to the 0, anything to the 0 power is always 1. So you have to be very careful on that problem. And then to simplify, we get 15 here. So I end up with 15 minus e to the third, and then we're subtracting a negative 1, which becomes addition. So this was the answer that was not present. And to compensate for my error, I gave everyone credit on this problem. So just be careful when you're evaluating e to the 0. That was one of the big reasons why we did this specific problem. Okay, really quick, I want to just talk to almost, well, over half of us. Over half of the students in the class right now are either at a P or a no credit. And a big reason for that, one of the largest reasons for that, is I have a handful of people that did not do quiz 6.1 yet. That was from last week. I have well over half of us that did not do the quiz on Monday. And I believe these are both equal to roughly 20 points. And then we've got missing homework. And some of you did not turn in the Unit 5 remediation. So if you're wondering, what can you do in the last, by the way, we only have, I think it was, let's see, 5, 4, 4, 2. So 8. We only have 15 days left of actual physical school days. That's not a lot. And half of those days you won't see me. So you have very little time to get this work in. And some of you really need to get some things completed and turn those in. Like I said, the quizzes, those you can do quiz corrections on as well. So if you get anything wrong on quiz 1 or quiz 2, do quiz corrections. And all you do is open up the quiz, correct the ones that you got wrong, and then send me an email of those corrections, and then I update your grade. A couple of you have already done that, so that's good, but I still have to grade those. Anyways, you need to make some kind of push here before the end of the trimester. Now, do keep in mind, all of this stuff, all the Unit 6 stuff is due next Wednesday. All right, we have our test on Friday next week, but it's actually for you guys, it's going to be assigned on Thursday next week. It's not due until February 15th, but all the Unit 6 stuff has to be in before we assign that test. So if you need help, come see me in my office hours. I'm available from 1 to 2 every day but Wednesday, and you can stop in and get help with this, or just if you need a plan for getting caught up, let's have a chat. But like I said, over half of us in this class have not done these items that are required. So some of us just have to get the ball moving. Okay, so we're gonna jump into the last section of this unit, and it's based off of properties of integrals, and then we're gonna mix in a couple more things here with the fundamental theorem of calculus today. So the big assumption is that you watched the video on Wednesday. If you didn't watch that, you have to go back and do that. All right, now these are the properties. I am not going to have you write these down, partially because these properties are basically the same kind of properties we dealt with derivatives. So they hopefully come more natural now because we've used them so often. I just want to make sure we kind of review some of the bigger concepts. Okay, and I'm going to go through this really quick, so don't write this down, but notice, what if I have an integral that goes from b to a, and then all of a sudden, I flip the bounds. When I flip the bounds, that means we're calculating the area in the opposite direction. We have to compensate for that, and we have to add the negative. So, when you switch or flip your bounds, you have to be very careful with that, making sure it's the opposite sign. By the way, one of the questions on the quiz had you calculate the area and the bounds were flipped. You always want the smaller number on bottom and the larger number on top. So if in this case, the larger number was down here and the smaller number was up top, we want to flip that because that always calculates from left to right. And when you flip it, it becomes negative. All right, this one we talked about, think of it as the area underneath the curve. If I go from A to A, there is no area, right? That is not a two-dimensional shape, that's a straight line. So there is no area, which means the integral is equal to 0. So notice how we have been making reference to integrals as the area under the curve. I think that's really important for you guys to understand that concept. All right, this one we saw with the example in the warm-up. We saw it twice. At one point it was pi, at one point it was the number 4. But if k is a constant and you're evaluating the integral, you can evaluate that constant by pulling out k and doing the integral and then taking this answer and timesing it by k at the end. So nothing super crazy there. I like to just think of this one as a constant multiplier. And again, your delta math assignment, the first part of it deals with these properties that we're talking about here. Okay, these next two are basically the same thing. It says if we have a function f plus g, and I'm evaluating it from a to b, well, then you can separate this and you can take the function f from a to b and the function g from the same bounds and evaluate them separately and then add those two areas together. Same thing with subtraction. Okay. If you want a more visual understanding of why that works, here's kind of just a quick visual understanding. Let's say I've got a graph that goes like this, and I go from A to, you know what, actually this one is not the one I wanted to do. Sorry, I don't want that. I think it's the next one. This is the one. Um, this one we've already actually alluded to in earlier days. So what if I have the area under the curve of f of x and I go from a to b, but then I have the same function f of x from b to c? Well, if these two pieces go from a all the way to c and b is the same, then a faster way of writing this is a to c. Okay, so let me show you a visual on this one just really quick. Let's say I've got a function here. Here's f of x, and I know that I got the area from a to b right here, the area underneath this curve. And then I've got the area from b to c, whatever that might look like. Well, instead of going from a to b and b to c and doing those separately, we can go from a all the way to c, and I can just calculate that area as one big integral. That's just a visualization of what these properties are kind of showing. This one actually did not get presented in Mr. Waffler's video, and I don't think you need to write it. I just want to show you this because it's kind of a visual, hopefully a visual common sense piece. The notation just is a little tricky. So let's say that I've got the area underneath the curve from a to b of f of x. Well, if I take the lowest value, and times it by the difference from a to b. So let's look at this as a visual here. And if I take the lowest value, so where is the lowest value? It's right here. That is the minimum of f of x. And then I multiply it by the difference from a to b, which is the width. Well, that's going to create a rectangle here. And we can find the area of any rectangle very quickly. Base times height. So that would kind of give me an area like this. Well, then what if I took the highest value? What if I took the maximum of f? So on this graph in between a and b, here's the largest piece. And if I do the difference from a to b, if I do the width again, that will give me a rectangle that looks like this. And I can find that area. Now you can tell that I'm going to purposely leave this unshaded, but the rectangle of the light blue shaded region is going to be smaller than, it's an underestimate of this integral, and the green value, the larger one taking the maximum and the width, is going to actually be larger than. So we know that our answer for this actual integral has to be somewhere between the minimum and the maximum. And that's really just kind of like a intermediate value theorem, where if I have a min and a max, I know my answer lies somewhere in between. But nothing super crazy there. And notice if I was to do rectangles here, this would be an underestimate, and this one would be an overestimate. So it makes sense that the actual answer is somewhere between the under and the overestimate. Okay, and then the last one, like I said, these are kind of common sense pieces. So what if you know that just the function, notice there's no integral symbol, so what if f is greater than g? Let's draw this graphically and just kind of think of this. So what if f goes like this? And on the entire domain, f will always be greater than g. And then g is somewhere right here. Okay? If this fact is true, then my conclusion is if I go from A to B, then the area underneath the curve of f, so this big area right here, will be greater than the area under G. Because under G would be from A to B, that would be the orange area, and you can definitely see that the area of f is larger than the area of B. So some of these properties are what I think common sense, but mathematically they're logical, and we do just have to have a reason for them. So, like I said, these are the properties that Mr. Waffler went over. The ones that he didn't go over are more just factual pieces that aren't really going to come up a ton. Okay, you will definitely want to write this down. Okay, now my goal here is to show you guys how this integral right here, the area under the curve from -1 to 4 of f of x dx, can be represented using the properties of integrals. And if we think of it in terms of those properties, it actually becomes a very friendly problem. But to help frame your mind, let's think of what this looks like graphically. Okay, we've got three pieces to this graph. Anything from -1 to 0 is represented by the function e to the x. The value at 2 is equal to 5. And then anything greater than 0 all the way to 4, except for 2, is going to be represented by the linear equation. So you don't have to draw this graph. This is just a visual so we can kind of get a sense of what we're doing. But let's look at the pieces. Right? The first piece right here goes from -1 to 0. Right? So I need to find the area under that curve. And then I've got exactly 1 point right here at x equals 2. And then everything else from 0 to 4, so from 0 to 4 is going to be represented as the area underneath this curve. Now notice, that 2 doesn't really affect this area at all. So what we can do is this. Let's rethink of how we want to do this integral. Instead of trying to find all the area under the curve, which we know mathematically we can't do, we're going to break this up. And how I'm going to break this up, I'm going to try to use my colors, is dealing with the first piece here, dealing with this domain from -1 to 0. So I'm going to go from -1 to 0 of f of x. Well, what is f of x at this point? It is e to the x. Right? And then we're going to add the area under the curve. Now notice right here, maybe I'll put this in, but it's not going to make sense. So you might not want to write this in red because I'm actually going to erase it. I have 2. Well, 2 to 2 of 5 dx. If I go from 2 to 2, if I just have this straight line here, that doesn't have any area, right? That answer is 0. So I'm actually not even going to put that in because it doesn't really help us in the context of this problem. Okay, so being evaluated at a single point, we can kind of ignore. And the reason why we can ignore it is I need the area under the curve from -1 to 4. Well, if I end at 0 here, that means I need to start at 0, and I need to go to the end of the interval, which fits the domain that's given here from 0 to 4. And then we have x plus 2 dx. So the area of the blue and the area of the green will give me the entire area under this function. So now, yes, I understand that we could calculate this using a trapezoid for the green. So if you wanted to, you could just do trapezoid area here. But I want to make sure we're really good at doing the antiderivatives as well. And if you watched the video, you actually know that you could do this in your calculator. I am going to show you that again today at the end of the hour, but there are times where you have to know how to evaluate this without a calculator as well. Okay, so let's evaluate the integral from -1 to 0 of e to the x dx. So I'm thinking, whose derivative gives me e to the x? Okay? Or the antiderivative of e to the x is itself. And then we're going to evaluate that from 0 to -1. And let's just finish this one all the way before we do the green one. So now that I have the antiderivative, I did not write the integral symbol. I wrote the evaluation bar. I'm going to evaluate the upper bound. And I know it's not going to really matter, but I like to put brackets around this so I don't ever screw up this negative. And then I've got the lower bound evaluated for x. Well, we know that e to the 0 is 1. And if I subtract e to the -1, we know we can write e to the -1 as 1 over e. So that's as far as I can take this one. Now we're going to deal with the area from 0 to 4 and add those answers together. Okay, so now I have two pieces here. Now, by the way, I don't write this because you'll see why it doesn't matter. These are two different functions, right? So if I wanted to, I could use the fact that I can take this integral separately plus this integral separately. But why? Right? Why not just take the antiderivative of each one and evaluate it at 4 and at 0 instead of doing them separately? So there is a point where some of those properties that we've taught you, you could use them, but it just makes things extra, and we don't need that. So let's do this just as one big integral. I'm thinking, whose derivative gives me x? Well, to do that, I have to add 1 up top, so I'll get an x squared. And if I get a squared up top, I have to multiply by the reciprocal of 1/2. Or some people just say divide by 2. So that's the antiderivative of x. And then I'm thinking, whose derivative gives me 2? Well, that's 2x. Then I need to evaluate both of those at 4 and at 0. So we always do the upper bound first. Notice I'm plugging in 4 into both spots. And then we've talked about this before. I didn't do it on this one because when I plugged 0 in, e to the 0 is not 0, it's 1. So I have to be really careful. But I do know if I'm plugging zeros into a polynomial, it's always going to end up being 0. So in that case, instead of just writing 1/2 times 0 squared plus 2 times 0, you could do that. But we know that this answer for sure is equal to 0. Just be careful. If you're not sure on it, write it out. And then we're just going to simplify. So 4 squared is 16, and half of 16 is 8. 2 times 4 is 8, and 8 plus 8 is 16. And then we have 1 plus 16, so that's 17 minus e to the 1. And it is always a good idea to write your final answer as what did they ask, right? I wanted the area under the curve from -1 to 4 of f of x dx, and the answer is 17 minus 1 divided by e. Okay, this I definitely want you to write down, and I'd like you to draw a rough sketch, and I apologize because this graph is a little blurry, but our goal is to really focus on this idea of the fundamental theorem of calculus part 1. And what that fundamental theorem of calculus part 1 says is if I have an integral of, let's say, a to x of f of t, and I want to take the derivative of that. You got a problem like this on your quiz. We know that the derivative and the integral are basically going to reduce each other out, and anything that's a constant doesn't matter, but anything that's a variable gets plugged in, and all that's technically left over is what is my function evaluated at this x. But we do have to kind of think of, we're also timesing by the chain rule. That's what we talked about last week. So that's what we're going to be using to help us solve this information here. So I'll give you a second to go ahead and write this. You don't have to write the red part down or what we just wrote here, but I want you to write down the instructions and the graph. And then we'll do these problems together based off of this information. All right, so our first goal is to determine what is g of 2. And when we look at g of 2, we have to think of, all right, well, we know that in this notation, g of 2 is just saying, well, what happens when x is 2? So if I write that out, g of 2 is equal to negative 1 to 2 of f of t dt. And we know from this unit that this is representing the area under the curve. Right? I need to find the area under the curve from negative 1 to 2. And that should be really quick, pretty friendly, since we don't have the function f. By the way, it's important to note that this is the graph of f. So that's what allows me to look at this graph. But I do know that this is a trapezoid, and it's got a base of 1, 2, 3. So a base of 3, we can call that base 1. Base 2 is equal to 1. And then the height is 2. Right, so I might throw that in there. The height is 2. We're just going to use our regular area formula. And we can simplify that and get 4. So if I'm asked to evaluate regular g, g is just area under the curve. So if I asked you to do g of negative 3, you would put a negative 3 up here. By the way, don't write this because we're not going to evaluate it all the way. But notice, if I asked you to do negative 3, I don't like those bounds because I'm evaluating the opposite direction. So the very first thing I'm going to do is I'm going to flip the signs. I'm going to put the smaller number on bottom, but if I flip them, then I know this answer is opposite of what it should be. So notice, if I went from negative 1 to 3, that area underneath this curve is going to be a 2 by 1. So actually, I can calculate this really quickly. It's a triangle, right? Base of 2 and a height of 1. That area is negative 1. But we're taking the opposite of it, so it's actually equal to positive 1 because of the direction that we're going. So anyways, that's how I would do a different point other than 2. And you just got to watch the bounds because if they're, you may have to flip them. Okay, but that's not the real reason why we're doing this problem. Now we're looking at this, and conceptually it's hard to think of this. Where is g increasing? Where is the area under this curve increasing starting at 1? Well, you might be able to view that. It's growing here, and then it gets negative here. But there's a better way to think of this that's more in line with what we've already learned. So definitely write this part here. When is g increasing? Well, let's think about this. If I asked you to figure out last trimester when a function was increasing, what we would have to do is we'd have to take the derivative of that function and figure out when the derivative is greater than 0. Well, this is a strong connection right now to the fundamental theorem of calculus, part 1, where if I take the derivative of this, we know that the integral and the derivative reduce each other out. So this is crucial for our explanation for everything else, is I need to make a connection to g and g prime. So what I'm going to do is I'm going to take the derivative of both sides here. And when I do that, we end up with g prime. And then we know that the derivative and the integral reduce each other out. Some people like to physically cross them out and say, okay, dx and the integral go away. And all that happens is if your variable's up top, you just plug that variable in, and I get the connection between g prime and the function f. Okay. Now, do remember, we went over this, so I'm not going to go over it thoroughly, but if it's a constant and I plugged a constant in and then took the derivative, that would always be 0. So that's why we ignore the constant and we only deal with the function. Well, what does this mean? Right? This is crucial. You need to have this written somewhere on your paper. If it's up here, that applies to everything. But you need to have the connection that this graph of f is actually the graph of g prime. That is a strong connection to how we're going to solve almost everything else on this page. So when is g increasing? Well, g is increasing when the derivative is greater than 0. So looking at this graph, this is the graph of the derivative. And anytime we are above the x-axis, I know that g prime is greater than 0. So any value that's above, so from negative 1 to 3, that's when the original function g is increasing. So how would I answer this problem? I would say g of x is increasing on the interval from negative 1 to 3. And then why? Because we know that g prime of x, which is equal to f of x. It's important to state that if you were asked to justify it, you need to make the connection that the graph of f is also the graph of g prime, and then we can say that is greater than 0. All right? Okay, so now, since we know that this is the graph of g prime, this one is a very quick problem. Where does g have critical values or critical points? Well, critical points are when the derivative is equal to 0. And since this is the graph of the derivatives, notice this point right here, this point right here, this point right here, and this point right here. Those are all spots where I cross the x-axis, which is the derivative being 0. So my answers are right there. Now I could also ask you, where is g decreasing? It's decreasing when it's below the x-axis, so it would be from negative 3 to negative 1 and 3 to 7. All right, and then the last piece. where does G have a maximum value? So we got to think, what do we know about maximum values? Well, G of X, G prime of X has to equal 0. Notice we already know those, so we know one of my answers here, or maybe more, is going to come from this list. It's the critical values. So maximums occur at critical values, and G prime changes signs from positive to negative. Or we could say it changes from increasing to decreasing. Okay? Now, you might notice how I'm approaching these problems too. I'm actually providing the reason why all of this works first. I'm thinking about why is it a maximum value, and then I'm using that to actually answer the problems. So now let's look, and I got to figure out if I go from positive to negative, or regular G goes from increasing to decreasing. Well, here I don't know if this is going to be a max or a min because of the way that there isn't anything on this side. But I do have a negative value because I'm below the x-axis. And I go from negative to positive here. So that means at -1, I go from decreasing slopes to increasing. That's a minimum on G at -1. And then here I go from positive to negative. Well, that is the maximum. So I know that there is a max at x equals 3. And my reason is because G prime is 0 and the sign changes from positive to negative. Okay? Now, your job today is to use graphs like this and the connection that the derivative of that G is also F. So this is also the graph of G prime. I want to show you a couple of things here next for the next kind of 12, 15 minutes that you don't need to write down. It's just going over some of the problems you're going to see on Delta Math today. And then I do have a connection here. And by the way, these notes will be posted in Schoology, so you don't have to go and write them. But what if I took the same graph and I calculated all of the values of G? So here, what if G was -3? And we already did that one, right? We said what was the area under this curve starting at -1? It's a +1 because we're going the opposite direction. But if I put in the integral, if I put -3, so all of these are the outputs. And it's just a table generated, and we found the area underneath each curve starting at -1 and going to all other points. Well, look at this one. Why is the area under the curve from -1 to 1 equal to 0? Because there's no area. And then let's go to, we just found out that the maximum is at 5. So that would be the area under here, and all of this part would have an area of 5, and that's going to be the largest area out of all of that. And then it would continue to go down. But if I did this and then I created a graph, notice, here's the graph of F. That's the one that was given, right? Which is basically, this is the graph of G prime right here. So I undid that graph and I actually created the graph of G right here. And notice, we know for sure that there's a maximum at x equals 3, and we actually know its output is 5 because that was the area underneath the curve from above. And then we saw that there was a minimum here at -1. And then we had our endpoints here, which we can't really tell a lot about those endpoints right now, but that's just a visual connection. Okay, so this is the part I wanted to show you, and I'm going to go through these really quick. But in Delta Math, you're going to have problems like this, and I want to show you how to deal with these problems. So they're telling us the function G is shown below. So you always want to make sure you know what your graph is. This is the graph of G. if f is equal to the area under the curve. So f is the integral of g, which is the area under the curve. Find the second derivative. Ooh, so how would I do that? Well, I would take the relationship that I know. Right? That's given, right? Just rewrite it. And then I want to take the derivative of it once. So we know the derivative of f is f prime. And then I know that the derivative and the integral are going to reduce each other out. Right? So this derivative and this integral reduce each other out, and basically the x goes in here. So it tells me if this is the graph of g, this is also the graph of f prime. Right? So it's important that you also know how f relates to this graph. But I don't want f prime, right? I want f double prime. So I have to take the derivative of this again, which means if I take the derivative of this, f double prime is equal to g prime, which, what is g prime? If this is the graph of g, then g prime is the slopes of the graph of g. That's what that means. So if I want to evaluate f double prime at -3, that means I need to find the slope of g at -3. So I'm going to take, this is the graph of g. I'm going to go over here to 3. Oh, sorry, -3. Actually, you know what? I want to change this. I want it to be +3. I do. I want that to be +3. I like that better. So what is the slope at +3? The slope at +3 is the slope of this line. Up 2 over 1. Up 2 over 1. So this slope is 2 over 1, which is function f double prime at 3. Okay? Now what if I asked you to do f double prime at -3? What if I did the original problem? Well, that was looking at the slopes at -3. And notice here, your slope on the left and the slope on the right are not the same. So it does not exist, or you could say undefined at that point. Okay? But the big connection is figuring out what does f double prime, how does it relate to the graph that was provided. Okay, let's look at another one. So I have to figure out g is the function defined by g now is the area under the curve of f. So this is the graph of f. And I have to find g of 3. Now, I don't actually have to find the actual answer here. So what if I plug 3 in there? And this is saying the area under the curve from -6 all the way to 3. Well, we're looking for the sign values here. They're not looking for the number. These are the values, the sign. So notice, area under the curve from here to here is negative. Area under the curve from here to here is negative. And then the area from here to here is positive. Well, overall, I've got more negative than I do positive. So I know that this answer, g of 3, is negative. Okay. Then they're asking me to find g prime of 3. Well, what is that? That means I have to understand what is g prime equal to. So I'm going to take the derivative of this side. So what if I take the derivative of g and the derivative here? And notice, that'll give me g prime, and then the derivative and the integral reduce out, and this x just pops in, So it just tells me that g of x is actually equal to f of x. So the graph of f is also the graph of g prime. So what is g of 3? Well, g prime of 3 is equal to f of 3, which is just the point. So that answer has an output of 0. So this answer would be negative. This one would be 0. And then I have to make the connection to what is g double prime. Well, g double prime is actually equal to f prime. So it's the slopes of this graph. So what are the slopes at 3? The slope of this tangent line right here is 0. If I drew a tangent line here, slope would be 0. And that's how I would fill these values in. They're going to ask you, is it positive, negative, or 0? Now, if I had my point elsewhere, like let's say it was right here at 7, then you would know that g double prime of 7 is positive because that's a positive slope. Okay. Let's look at, we can probably do one more for sure. So this problem is asking us to determine where g is concave down. So if I'm going to do when g is concave down, I know the second derivative must be negative. So I have to just do the same work we did, and we have to figure out how does this graph that we're looking at relate to the second derivative. So I'm just going to do this. I'm going to take the derivative of this side, and the derivative of this side reduces out, and it tells me that this graph of f of x is also the graph of g prime. So then what if I take the derivative again, and that tells me that g double prime is the same, that looks kind of funny, is the same as the slopes of this graph. So I need to figure out when is this value negative. Right? When do I have negative slopes? And that's pretty quick to find. Where are the slopes negative? When does f have negative slopes? That's what this is looking for. So increasing, increasing, I've got a negative slope here. Increasing, 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 we've got negative slopes here. Increasing, increasing. So where do I have negative slopes on this graph? From negative 7 to negative 5. And from negative 2 to 5. Positive 2 to 5. Okay. So notice, you have to know the fundamental theorem of calculus before you can make conclusions about this, and your goal is to figure out how does the graph given relate to the function g, and it's all from the fundamental theorem of calculus. I got one last one that I think I can get through. And then what we're going to do is, I told you I'd talk about how to do this in your calculator. You don't need that for today. So next week we're going to talk, just reconnect with how to do integrals in your calculator. But that was all from the video from Wednesday. So, all right, let me just do this one. and then we'll be done. Our goal is to write the equation of the tangent line at g equals 0. Well, g is equal to the area under the curve. So what do I need? I need a point, and I need a slope. Anytime you see write the equation of the tangent line, we haven't done this in a while, I need the point of g of 0. Well, that's just plugging 0 in here and here. So g of 0 is really the area under the curve from -9 to 0. So here's -9, here's 0. Then we're just going to find the area underneath these curves. However, this is kind of split up. I've got to find the area of each little piece because I need to split it up into familiar pieces. So I'm going to do this as a rectangle, a 2 by 1, 2, 3, 4, 5, 6. So this is 6 by 2, which is 12, but notice it's below, so that's a negative. And then this is a 6 by 2 triangle, which is 6, but it's below the x-axis, so that's negative as well. And then this is a 1 by 2. So if I calculated this area, it would be -1. So if I add up all of these pieces, I know I get -19. But that's not it, right? Because then I have this piece that's above the x-axis, that's a 4 by 2 triangle, and 2 times 4 is 8, cut in half, tells me that it's a +4. So I know that my point, when x is 0, there's x1, y1. My output is 15. So I know part of my equation already. And then I need the slope. I got to figure out what is g prime of x. Well, that's the derivative of this. And g prime of x is equal to f of x. So I need to just figure out what is f of 0. And that's just reading the graph. F of 0 is equal to 4. So that's my slope. Right? And then the last part, if I plug in y1 is -15, my slope was 4, x was 0. You could leave it like this or solve. Okay, so I love these problems because they review max, min, increasing, decreasing, write the equation of the tangent line, all the things that we should be really familiar with. All right, homework tonight, 6-4 day 1, it's in Delta Math, and it reviews a lot of what we just talked about, plus the properties of integrals. That's all I have. Please get caught up on any of the work that you're missing, quizzes, homework, all that, and I'll be available from 1 to 2 if you need any help.